In this podcast, we'll be looking at refraction, or the bending of light. I'd like to start out by showing you some everyday examples of refraction. Here's an example of two glasses of water in front of different backgrounds, and you can see how the backgrounds have become distorted by the water inside the glass. What I'd like you to think about is why this happens. Here's another example. This is a picture from Life magazine. It's a girl in a pool of water, and it looks like her head has separated from her body. Obviously, this has not really happened, but it's due to the refraction of light. Here's another example. Someone's cleaning out a pool. You can see the pool cleaner, or this pole, going into the water, and then at the boundary of the water, the pole appears to bend. And this, again, is due to the refraction of light. So the bending of light, refraction is the bending of light as it travels through the boundary of two different media. And it occurs because the velocity of light slows down, or it could speed up, depending on the medium. I'd like to do a little example with you. Let's pretend we're not working with light for a minute. Let's pretend you've got a go-kart or a car, a four-wheeled vehicle, and you're driving on concrete. Concrete is relatively smooth, and the car goes pretty fast, or the go-kart goes pretty fast. But what happens, travel along this path, what happens when you get to grass, when you're traveling at an angle? This wheel, the right wheel or passenger side wheel, would hit the grass first and slow down. This wheel doesn't hit the grass until it goes a little bit farther. So what ends up happening is, because the passenger side wheel slows down first, the direction of travel of the car will actually change. And the way that we define this direction change is to draw what we call a normal. Oh goodness, let me try that again. A normal, N-O-R-M-A-L, which is perpendicular. And what we say is that the direction of the car bends toward the normal. This new angle is smaller than our original angle. And this is what happens when light travels from air, where it travels relatively quickly, to glass. So if we have a ray of light traveling in air and it hits glass, what's going to happen is that the light is going to slow down. The light's going faster here. It's going slower here. And when that light slows down due to hitting the glass, it's going to bend toward our normal line. So let's label a few things. This angle, this first angle, is called the incident angle. The second angle, as measured from the normal, is called our refracted angle. It turns out that based on this phenomenon, we can measure something called the Index of Refraction for different media. The Index of Refraction, N, is a ratio of the speed of light in a vacuum divided by the speed of light in your medium. So let me give you a quick example there. If the speed of light in a vacuum is 3 times 10 to the 8th, and let's say that we have a special kind of glass that, all glass will slow light down. And let's say the light slows down to 2 times 10 to the 8th meters per second. We would say that the index of refraction for that substance was 3/2, or 1.5. This index of refraction has no unit. And again, it is just a ratio of the speed of light in a vacuum to the speed of light in your medium. The speed of light and the index of refraction both lead to something called Snell's law. Snell's law gives us the relationship between the angles in my top diagram here, my angle of incidence and my angle of refraction, and the indices of refraction. Snell's law says that the incident index of refraction times the sine of the angle of incidence equals the index of refraction of the second substance times the sine of the angle of refraction. You'll be doing a lab involving Snell's law that will make this more clear, but here's the big takeaway that we want you to get. Light will be refracted toward the normal when it slows down. So in my example, we went from air to glass, the light slowed down, and the light bent toward the normal. When the reverse happens, the light will be refracted away from the normal. So when it speeds up, so for an example, if light went from water into air, that would cause it to speed up, and it would bend away from the normal. Let's try an example problem. A light ray strikes an air-water surface at an angle of 46 degrees with respect to the normal. Given that the index of refraction of water is 1.33, find the refraction angles when the direction of the ray is from air to water and from water to air. Okay, so this is actually two problems. I'm going to start out this way, air, then water. Index of refraction for air is approximately 1, and they tell us here that the index of refraction for water is 1.33. I'm going to sketch a diagram. There's my normal, and then my light ray, they say, is coming in at 46 degrees with respect to the normal. That's my angle of incidence, and I'm supposed to find my angle of refraction. I know it's going to be smaller than my angle of incidence, and I'm going to actually calculate it. Snell's law tells me this. Rewrite Snell's law. Ni sine theta I equals Nr sine theta R. Okay, so we're going to do 1 times the sine of 46. Those are my values for air, equals 1.33 times the sine of my unknown refracted angle. And now I'm going to do the math. I'm going to take the sine of 46. I'm going to make sure my calculator is in degrees. So the sine of 46. And then I'm going to divide by 1.33. And then I'm going to take the inverse sine. And I get 32.74. So I've calculated that refracted angle. Couple of things here. If I were to turn the light ray around, in other words, if I were to have the light ray traveling at an angle of 32.74 degrees and then exit from water to air, I would end up with exactly the same angles. But that's not quite what the problem is asking me to do. The problem is asking me to solve it again, but this time this time my incident angle is in the water, and that's 46 degrees. And now I've got to find the refracted angle. So what I've done is set up the problem and written out Snell's law. 1.33 times the sine of 46 degrees equals 1 times the sine of the refracted angle. I solved for the refracted angle, and it's 73.08 degrees. And what we see here is that when light is traveling from water out into air, when light speeds up, it bends away from the normal. And this is the opposite of what we saw in the first example. When we go from air into water, it bends toward the normal.